Hi guys, I wanted to make a real quick review video on the diagram part of discussion exercise number 5. I noticed that a lot of people mixed up the leading and the lagging strands, and I really want to make sure that you guys are clear on how to do this. So I'm just going to go through it real quick. I'm going to show you the way that I do it, the approach that I take. I think it's really intuitive and really easy to learn, very quick. So I think that in terms of the exam being in 3 days, just learning this approach that I'm teaching you will be really, really helpful, even though there are technically multiple ways that you could go about it and get the right answer. Okay, so just a reminder, first of all, that every nucleotide is going to have that 5' and 3' end. So when we're talking about a 5' and 3' end of a sequence that we're looking at, it's all going to be relative to each other, essentially. And I'll show you what I mean. So say that we're looking at this huge strand up here, this giant strand. You can see, okay, clearly this end is going to be 3' up here, 5' down here, and then opposite on this side. So 5' up here, 3' down here. And now let's say we decided, oh, actually we only care about this one section of the genome. So we're just going to look at that instead. So we're going to physically be changing the spots that we're looking at. But each side of the strand is still going to have that, that relationship where we have that 3' over here, 5' over here, and then opposite down here. So even though we're physically changing the spot that we're looking at, we still have that ultimate relationship with each other. So now let's say we have this sequence, but we want to split it in half and look at each of those halves separately. So let's pretend that we're going to have this imaginary line down the middle, and we're going to be looking at each of these in isolation of each other. So we have this side here, which we can see from the original, still has this 3' and 5' end here. But now we know that even though we physically are changing where we're looking at the end point, before it was here and now it's here, relative to this 3', this end is still going to be 5'. Relative to this 5', this is still going to be 3'. And then same with this other half. With this other half, we know that this side still has to have that 5' and 3'. But now we know that relative to that, this is going to be 3' up here, 5' up here. And so when you look at them together, you can see that these ends are, even though they're referring to like the same physical space, since each nucleotide has that 5' and 3' end, we're able to have those right next to each other because we're just identifying which spot we're looking at when we're splitting up the two strands. So no matter how you split up the genome and like what you're looking at, you're always going to be able to have this relationship of having one side be 3' and one side be 5'. So you can essentially think of each section that you are caring about at a particular moment in time as kind of like a microcosm of the entire strand. So if we look at this, we can see that it has the same directional relationship as this huge strand, even though we did multiple things. We first just looked at this, and then we just looked at this. So we're still having that same exact relationship. And in just a second, I'll be able to show where people really went wrong with this in terms of the exercise, and hopefully that will kind of clear things up for you. So yeah, just a reminder that there are multiple ways to approach this, but I think that if you follow these steps particularly, you will be good to go. So this was the diagram that we were actually given in the exercise. And so essentially this picture is the same as this one, except it just has that replication bubble being shown. So we are given this 3' and 5', and then 5' and 3' over here. And now what we know and what we should do first, I'm gonna move myself up here, is always split this replication bubble down the middle, because remember that in eukaryotes, the origin of replication is going to be bidirectional. We're going to have both replication forks going at the same time, but in different directions. This will speed up the length of time that it takes to replicate the DNA. So what I would physically do as your first step is to physically draw this line in, and then physically draw the arrows that indicate the direction that the origin of replication is going in. And remember that it's always going to be pointing towards that the fork. So it's always going to be like stemming outwards from the origin of replication. So after we have that physically drawn in, then what I recommend doing is physically covering up one side of the bubble, the side that you're not working on right now, because just having that side I think is going to be really confusing for people. So just cover that up. Don't worry about it right now. And so now we have this. We know that this side is 3'. And we know that in order for synthesis to occur, this has to be 5' because we have to have that same directional relationship where we have one side 3', one side 5'. If we had both 3' here, then there really wouldn't be any anything pushing that reaction, because there's going to be no like 5' to 3' directional flow. It's just 3'. So that's why we know that this has to be 5'. And then similar to here, we see that this is 5'. So this end over here has to be 3' to maintain that directional relationship. Okay, and so remember that those are for the template strand. But what we really care about is the synthesis of the new strand, because that's what we're trying to determine. So remember that it's just going to be opposite of whatever the template strand is. So we know that, okay, 3' here means 5' here, 5' here means 3' here. And then we know that exact same directional relationship is going to apply from this side of the strand to this side of the strand. So we can say, okay, 5', then this must be 3'. 3', this must be 5'. And so really just thinking to yourself, okay, am I maintaining that, that original relationship? Like, is this still acting as a microcosm of the entire strand? And you can see that here. And you can see that here. Okay. All right, so now what I like to do is say, okay, we know that synthesis is always going to happen 5' to 3' direction. So I'm just going to draw little miniature arrows showing which direction that is for each of the strands. So you can say, okay, 5' to 3', draw this little arrow. 5' to 3', draw this little arrow. And now what we can do, since we physically drew the direction of the origin of replication, this is going to be really easy. It doesn't require much active thought at this point. We can just say which strand has the direction of synthesis that matches the direction of the origin of replication. And so we can see clearly that this direction and this direction match, which means that the cell isn't going to have to do any additional work to make this occur, because it's naturally going to be synthesizing the direction that the origin of replication is going. So this is going to be the leading strand. Whatever strand has that exact same direction is going to be the leading strand. The one that's opposite is going to have to be the lagging strand, because it's going to have to do that a little bit of additional work, because we know that synthesis always has to go 5' to 3'. So it's still going to have to go this way, but it doesn't really want to, because the origin of replication is pushing against it. And so that's why we have to do that, that pattern of adding those, of doing this like a section at a time, rather than just in this simultaneous strand. So that's why we know that this is the lagging strand. Okay, so now this is all labeled and done, and we're good to go with that. So now we can just repeat that process with the other side. So you can try to pause this video and try to do this side on your own. And then when you're done with it, you can press play again and watch and see if you were able to get it right. Okay, so it's the same exact thing. So we think, okay, this strand here is 3'. And so to maintain that relationship, because we're looking only at the strand, this section of the big genome, we still have to make sure that it maintains that relationship of having one side be 3', one side be 5'. So this has to be 5', we know that. And then same with up here, since this side is 5', we know that this is gonna have to be 3' in order to maintain that relationship. Okay. And then same thing with the newly synthesized strand, because that's the direction that we care about. So we know that this is gonna be 3', this is gonna be 5'. And then again, same thing, the other end of that newly synthesized strand is going to be opposite of whatever it started with, because we still always have to maintain that relationship, that directional relationship. And then we can draw those arrows in. We know that synthesis is going to happen 5' to 3' no matter what. So we can just draw in the direction 5' to 3', 5' to 3'. And then simply circle the arrow that matches with the direction of the origin of replication. So we can see here, these arrows match. This one does not. So what that means is that we know that this one's going to be the leading strand, because there's going to be no extra work that needs to be done. This one is going to have to do it in segments, because it still has to synthesize this way, but it really doesn't want to, because the origin is pushing this way. So this is going to be the lagging strand. So now, if we uncover the other side, we can see the whole picture. And so this is what the answer key said. So if you looked at the key, this is going to be the exact same thing here. And so I think the part that people really got tripped up on here is by not thinking relationally and just thinking in terms of the entire strand as a whole. So I saw that a lot of people said that this was 3' and this was 5', which is opposite of what it actually is. And I think it's because if you look at this whole strand, you say 3' on this end and 5' on this end, if you're just like putting it in half, then oh, this must still be on the 3' side, and so it has to be 3'. And this is still on the 5' side, so it has to be 5'. But the reason why that's not right is because we're looking you can see that at this origin of replication, these regions are systematically different from each other now because the directions of replication are opposite of each other. And so if we had 3' here and 3' here, that wouldn't work in terms of synthesis because you have to have one of each of those sides in order for elongation to happen. So ultimately, it's really just better to think, what region am I looking at specifically? And do I have that 3' and 5' relationship in that region? So if we're only looking at this side, then we need to make sure that we have one of each for both of these, and then one of each for both of these. And I think that just getting that part right would really help with people being able to get the right answer. I still think it's a really good idea to physically draw these arrows in, the arrows of the origin of replication and the arrows of the direction of the new strand. But even if you still get these original ones right, it's easier to mess up if you're just trying to remember it in your head, rather than just like physically having an arrow that you can just be like, yep, matches, yep, doesn't match. So hopefully that makes a little bit more sense. If you guys have any questions for me still, I'm happy to go over it more with you. Hopefully this is helpful for you. Thank you.